Right. Perfect. Out of the 80 odd people, it looks like just a handful of people here. Do people want to start introducing themselves, whether they're on the engineering side, background, and hopefully we can have some interesting, useful discussions. Anyone want to volunteer to go first?
I'll volunteer. So hello.
Thanks, Adrian.
Hello, everybody. My name's Adrian. I am from mechanical engineering, and I work on sensors, specifically chemical sensors. And in the last couple of years, that sort of like is focused on wearable chemical sensors that can measure interstitial fluid. And I suppose the thing I'm sort of most interested in today and why I sort of come along is I'm interested to know what sort of things clinicians are interested in terms of chemical biomarkers, what things would they like to measure that they can't measure, and so on.
Perfect. For those of you who just joined, we're just, because there are only a few of us, we'd sort of start to go around introductions if anyone else wants to volunteer before I pick on people.
So I'm happy to go ahead.
Super.
So my name is Ali Masoudi. I'm a senior research fellow at the Optoelectronic Research Center, ORC. So our main activities is with lasers and fiber optics and optical sensors. So the area that I'm working with is quite different than most of the conventional sensors, as if it's what we call a distributed sensor. So we use a optical fiber, a single strand of optical fiber, and we can measure variety of physical phenomena like a vibration, temperature, a strain, all along the fiber from a single point. So if you have access to one end of the fiber, you should be able to measure, let's say, temperature every centimeter all along 10, 20, 100 centimeter, 100 meters of fiber, which is equivalent of having hundreds or tens of thousands of sensors using a single fiber. So that's my area of expertise.
Super, thanks. I mean, if there are any clinicians on that think that would be interesting or useful, do feel free to introduce yourself, speak. So this is... Sorry, I interrupted someone.
I'm happy to introduce myself. I'm Becky Cusack. I'm one of the ITU consultants. Particularly interested in rehabilitation, and the problem we have at the moment is a metabolic demand of patients as we get them mobilizing while on a ventilator. The methods we have so far aren't particularly accurate at doing this, and we're moving very much towards prescription rehabilitation so that we can try and push the patients as hard as we can without causing pushing them too far with the metabolic reserve that they've got. Along with this, we also have sedation, which actually inhibits getting the patients moving. If they're too heavily sedated, obviously we can't get them sitting up on the edge of the bed. So depth of sedation is something else which would be very good to monitor. And thirdly, these patients also suffer with a delirium, so cerebral functioning measurement would be quite interesting to look at to see if there's any way that we can monitor getting patients awake without being confused.
So how is metabolism monitored at the moment then? You need something that's more accurate or
so at the moment we can look at oxygen usage, but it's quite invasive, so using arterial and venous oxygen sampling, and then we've got quite crude usage of sort of blood pH. Lactate tends to go up very late and it's sort of very non-specific, so to look at localized muscle demands would be quite useful.
Well, so I'm running the room, but if people want to sort of jump in, feel free, and I'm happy to take a seat back. Does anyone want to step in at this point? Anyone can measure those sorts of things? If not, Francesco, you got your hand up?
Yeah, I was just going to introduce myself. I am a hematologist. I'm interested really in how to investigate the interactions within the complex structures of lymph nodes, where there is there are many different cells, in a way sensing one to the other through multiple receptors, not one independent from the other. And so the models that is very much appealing now to the medical scientific audience is what are called organoids. And there are complexities which are very much dependent on what the topic of interest is for the clinician, for the or clinician scientist. In my case, it is interaction between sugars on the B cell receptor of the B cell and lectins on macrophages within a very much more complex setting of other cells, T cells, dendritic cells, follicular helper cells that make and tissue stroma that make the system rather complex.
So you want to do that at the single cell level? This is sort of cell layers, organoids are 3D.
We want to do it at 3D level. So while having a 3D model, that allows interaction of different complex receptors, in that context, to look at what happens to one specific receptor, very one. This is what we keep being asked in papers once we review, once we submit them. So the interaction with the engineer would be massively important.
So you need to look at imaging for single molecule
We need to look at imaging, yes, but in the specific case of organoids, we need to look at how these cells move within the organoids, depending on that interaction, or don't move within with reagents that are leading to the engagement or blocking the engagement within that specific lectin-sugar interaction. We need to see what happens in terms of signaling within the 3D model.
Really interesting.
Who knows how to do that?
Do we have any engineers on who work in imaging and some of the technologies like STORM for single molecule imaging?
Mm-hmm.
Anyone say?
Of course, we could always recommend the biophotonics group from Sumit Mahajan here in Building 85. So this might be very relevant to his kind of thing.
What's her name? Say it again.
Sumit Mahajan. He's professor of biophotonics.
Biophotonics.
Well, you know, it's the latest name for these things. But I also popped my camera on because I have to go soon. But I did recognize between the various chats that there might be a nice link between Adrian, who's at the bottom of my screen, and Michael Arden-Jones. There seems to be a nice fit with your guys' interests, which links to Cesar Nui. So that's my kind of effort at playing Cupid. And I just got to go, guys. Sorry. Thanks, Dan, for organising.
You've got one more minute, Jonathan. Introduce what you do and what you're interested in.
Yeah, microfluidics, precision single cell handling, or precision volume handling, and it really comes down to getting better data out of your sample. A lot of it is applied on a discovery angle, but there's a clear pipeline by working with clinicians, people like Francesco, how you turn that discovery type data or tool into something that can be translated into real world use. So ultimately it could be diagnostics. For example, we have one on identifying hypersensitive platelets which drive platelet behavior as a collective. Are those, for example, are they prognostic for thrombosis? So that's the kind of thing we do, but it touches on many things, including Francesco's work on single cell transcriptomics. But it'd be lovely to link transcriptome, epigenome, proteome.
Yes.
But yeah, I'm kind of got to go. That's very kind of you, Dan, to give me a little, what do you call it? A box to stand on. I forget what kind of box, but I'll let you guys get on with it. And thanks again, Dan, for running the show. Right? Okay. Yeah. Bye, guys. Speak to you later, Francesco. By the way, I'm following up with your.
Speak to you later, John. Yes, indeed.
Cool.
Thank you.
So,
and Dan, I think I'll if
yeah, no problem. We could chat later.
Great. Thank you.
Super. For those of you who've just walked in, thanks very much for joining us. We're doing sort of introductions, and if someone introduces and then says a challenge or I have a technology, try and do that matching. Thanks, Michael.
Yeah, hi. So I just spoke earlier for a minute on one slide, but yeah, and I'm grateful for the introduction to Adrian. We actually made contact through email anyway. But the thing I'd be interested to pose to this group is that what I'm particularly interested in is real-time live human imaging, sensing. So I mean sensing in the context of imaging, and I think that I've worked on model systems, in vitro models and things, and I've been burnt by some of them. And I think that the latest sort of advances we've got in this sort of area to apply that to real-time human data, I think is really where the cutting edge of sensing lies, and we can really make great strides here. There's a fantastic group here. So if anyone's particularly interested in that, so the link with Adrian is about sampling, which is potentially really exciting too, micro sampling live. But I'm also interested, particularly with the skin, there's a great application for measuring all sorts of things, or sensing all sorts of things, from all the older approaches with electrical impedance, but other sort of photonic aspects and imaging that could sense real-time imaging. And these could be applied to some of the great challenges we've got in skin disease at the moment, which is that skin diseases are really common, but what we don't understand is why some people are severely affected and other people suddenly have severe flares. So it's about disease monitoring, and it's about prediction of severe disease. And then in addition to that, it might surprise some of you to know that the latest therapies in skin disease are really expensive. We're talking something like £100,000 a year for some patients having skin disease type treatments. So actually monitoring response to treatment is becoming increasingly important. And I think with sensing technologies, we could really do that. So that's my little spiel, and I'd be really interested to hear anyone who's interested in that too.
Does anyone want to follow up on that? I know we've got people from Zephyr Institute and Photonics, Graham, for example, Mylan.
Yeah, well, I can say something. I'm not sure I can address that particular problem, but there are two things of interest, possibly, that we can do, I think. So the first is there's an obvious link to clinical applications. So we've just got a grant with Solfast that's looking at healthcare and also environmental monitoring. And the idea is that we make sensors and sensor chips very low cost. So I work in something called silicon photonics, which is optical waveguide based circuits on a chip. And because it's silicon, it can be mass produced at very low cost in principle, just like electronics. Obviously, silicon is electronics as well. Now the grant we've just got is involves a number of universities and, as I said, the clinical and the environmental monitoring. But it's basically a technique to extend the wavelength range of the chips that we use for communications into the mid-infrared, because of the specific absorption lines that are stronger in the mid-infrared for identifying things like, drugs or proteins or whatever it is. So we have targeted at the moment cancer monitoring and drug concentration monitoring, largely driven by Saul and his the people he has communicated with. And then on the environmental side, it's gases at ocean surfaces because of the again really who we're interacting with on that. But I mention that because I wonder whether there's potentially gas measurement applications in some of the things I was hearing earlier, possibly about lungs and so on. Now this grant is literally just announced, so you know, we haven't actually begun yet. But the reason I mention that is that what we want to do is produce demonstrator chips and so on. So in principle, because you're measuring a spectrum and a whole series of absorption lines, as it were, it should be very widely applicable, and it should be very low cost. So it should enable things like almost real-time measurement rather than sending samples away. And so we're thinking about liquid being put on chips such as blood or even dried blood and various things. And so, as I say, we've chosen some applications based on Saul's advice, but I think it could potentially be more widely applicable. So what I was thinking about how we might bring this forward is once we're a little bit further down the line with some of these devices, is then coming back to this group and showing preliminary results and perhaps how it might be applied more widely and so on. But the idea is that in principle, the optical chip itself will be of the order of a centimetre square. So very small. There will be some optical I/O in out to get the signal on off chip, and there'll probably be some electronic connection to to manipulate the signals and so on. So it will end up being a bit bigger than that, but it's essentially a spectrometer type measurement on a chip. So you can imagine a box about maybe 6 inches square at the end of the day, something like that. So small, portable, low cost, really doing things like monitoring, keeping people out of hospital, perhaps doing scanning in advance for monitoring of diseases or something like that. So that's that one. I'm obviously happy to give you more details if anyone wants any, but as I say, the grant hasn't started yet, but obviously we have ideas about how this will go. Now, the other thing that came up in the chat afterwards, during the discussions earlier, was that someone was looking for distance measurement for fetal monitoring. And so another piece of work we're doing came to mind, and that is that we're doing some 3D imaging via LiDAR with a startup company. And already, the collective team have published the best data in the industry. And what that means is that at distance, it doesn't have to be at distance, but at distance, if you wish, you can measure small movements, for example. So one thing we've done already, just as a demonstration, was to measure breathing at 40 meters. So in other words, you get millimeter accuracy of the movement at distance. But if you go closer, you can trade off the performances. And so this is why I thought possibly fetal movement would be something we could apply that to. Didn't even occur to me that might be of interest. It just, it just came out in the discussion. So if there's anyone else who needs to monitor small movements, possibly at distance, but not necessarily, this might be a way of doing it. But other things that 3D imaging is used for are things like face recognition on your iPad. But that's a very primitive version of LiDAR. We can do much better than that in principle, although it is quite early days. And so if you wanted, some sort of 3D monitoring, then this might be a reason. Now, the reason I said we couldn't possibly answer Michael's question is that it's not like a camera where you get detailed physical images. What you do is you build up a 3D representation of a scene. So you don't get fantastic high resolution images of skin, for example, but you can detect movement at a very high resolution. You can, it's really the sort of thing that's a very common application is for self-driving cars, for example, So you build up a 3D image, but what is becoming abundantly clear is because of the resolution we can achieve, it doesn't have to be at distance. It can be, it can be over 6 inches or even less, or a foot, or whatever you want. But you would tailor your system to do that sort of thing. It's not a snapshot like a camera, because you build up the image, you do a scan of the area, and then you use software to build up that image and reconstruct it. But you can, as I keep saying, get pretty high resolutions. So if you need to measure depth or movement or something like that for some clinical application, there may be this is a possible way of doing it. And as I say, it hadn't even occurred to me before I came on this morning that this might be useful in healthcare, but it seems like it might be now.
Really interesting. Thanks very much, Graham. Do any of perhaps on the clinician side want to step in directly, ask Graham any more questions? If not, there's been some interesting discussion in the chat, maybe. So Rob Wood, going back to the skin sensing with Michael, or maybe Nick wants to come in and say something.
Yeah, no, I can. I mean, this goes back a bit when we were chatting to Eugene Healy, and Rolls-Royce were interested in going into healthcare. So we had and still are working on electrostatic sensing for charge patterns on surfaces that are rubbed together for some mechanical systems. But the idea was to have a look to see whether we can detect different skin properties that are sort of related to charge, dielectric differences, and we thought we could look at slightly penetrating into the skin like sensors to scan and see differences that might relate to cancerous issues of the skin. But we tried to get as far as putting an ethics approval in, but then Rolls-Royce backed away from that investment. But if it's of interest, I'm sure Nick and I could meet with Michael and we could see whether there's legs in it.
Yeah, you're still on the call, Michael.
Yeah. Sorry, I just turned my camera off to try and sort of don't want to take all the focus off me. But yeah, that'd be great. Thanks very much, Robert. I'd like to do that.
Okay.
Have those properties ever been explored? Is it likely to be something that works?
Well, I mean, we're trying to explore it for mechanical systems. So, I mean, it's just, we don't know. So we would need some funding, and we probably need some trials, but we need to make the sensors to attach onto the skin first. But the electronics is sort of on its way, I think. Is that right, Nick?
Yeah, it's on its way. The one thing I'd like to say about this is that it might be possible to combine some ultrasonics and some electrostatic or capacitance sensing in the same kind of array, so we can get a dual modality and try and fuse the data. We've got this piezoelectric printable ink that's been kicking around for many years now, which can generate ultrasound. It's been looking for a home, and we've toyed with the idea of using it for imaging, but we haven't really had an application for it. And it might well be that this skin problem may be amenable to ultrasonic imaging for small depths, as well as capacitive imaging at the same level, and combining the two together. And I don't think it's that tricky a thing to actually implement, because we're looking for things that aren't moving very fast, so we can do individual pixel detection at a time and build up images by not in parallel, but in series. So the electronics would not necessarily be too onerous, like a sort of a traditional ultrasonic scanner. We could just do it a single pixel at a time and create an image slowly. So that might be quite an interesting thing to investigate. At the moment, I've no idea if it would work in the skin because I don't know what skin's like. But if we have a meeting afterwards at some point, we can probably discuss that and see if there's any mileage in it.
Thank you very much. That'd be great.
Super. Thanks very much. We've heard quite a bit from some of the engineers, but are there any other clinicians or people working in the health sciences want to step in at all? Introduce maybe some of the challenges or even the biggest innovations in their field? Silent, fantastic. Hopefully, if you are there and just struggling to unmute. Graham, go ahead.
Well, I don't have a response to that, but what I was just going to say that it might be worth just adding for everyone's benefit is that EPSRC seems to have a real appetite for healthcare applications at the moment. You know, they're almost pushing it to sort of regular EPSRC subscribers, as it were. So, I mean, healthcare has always been one of their 4 prosperity outcomes, but they seem to particularly have an appetite at the moment. I don't really know why, but if you can come up with projects, now is probably a good time. Is all I really want to say.
Thanks very much. So right at the start we did sort of some introductions and we started hearing from a few different people what they're interested in, what they're developing. Does anyone want to step in, introduce themselves before I do that job for you and pick on someone? Being really mean. So, out of random, Fang, do you want to introduce yourself, say a little bit about what you're interested in, whether you're after applications or what your technology does? Thanks very much.
Okay, thank you for picking. I just joined. So my name is Xu Fan. So I'm a lecturer in the ECS. So my background is on nanoelectronics and nanophotonics. So my interest so I think the only connection of my work and with so the medical related sensor is through the collaboration with Nick Green. Nick Green is also in the audience. We just had a brief meeting with our PhD students and then we came back. So what we are trying to do is to find this niche field where we can embed these nanophotonic structures at the bottom of so now a microfluidic channel. So Dan was the examiner for my student, and he knows a bit about the work. So currently what we can do, so we last year we had 2 publications, so Nick and myself and our students, and with some collaborators in Japan and Singapore. So what we have achieved now is that we can have this kind of design, so nanostructures at the bottom of the microfluidic channel, and we can shine light on the microfluidic channel, and by using the light reflection from these nanostructures, we can control the nanoparticles in the microfluidic channel. So that's a very, in terms of technology readiness level, that's quite low. And we're trying to demonstrate this phenomenon in-house lab. So and then at the same time, because of this lockdown, the experiment is a bit slow. But on the other hand, we have the benefit of thinking more about the project, so different designs. So I think we recently have a quite interesting breakthrough. I think that we are going to have some kind of sorting that for as far as we know, it's not possible for other technologies. So purely, like say, only optical structures can do that. So yeah, that's kind of state we have. So probably a bit very far from our medical colleagues. Yeah, but yeah, we are here to learn from our medical colleagues. That's our situation. Yeah, thank you.
Thanks, you. Does anyone come up with any uses for manipulating single particles at high resolutions?
Yeah, so what we are thinking that is okay, I'll just talk about the fancy stuff we are just working on. I'm not going to talk about the two pieces of what we just finished. So what we are thinking that for fluorescence-based sorting, that's quite a useful technique. And the speed is inherently limited by the factor that you have to see the color itself, see the color from the particle, then you make a judgment. So no matter how fast your electronics is going to be, there's inherent some limitation. So we want to do this automatic sorting. So that's kind of like say very, I would say, a unique angle that we are going to enter this field. So automatic fluorescence sorting based on light, using light. Yeah, Nick, if you want to add more, yeah, so that's the project we're currently working on, and we recently had some breakthrough on that. We think that it's possible.
Looks like Nick's hiding. That's fine. I've just been looking down the list of the people left in the room, and thanks very much for staying to the end. Sarah Figueroli, looks like you're in allied health professions, maybe on that side. I wondered if you wanted to say maybe what some of the challenges are, if you're still around. Okay. So as many of you might have seen a pop-up at the start of the top of the screen, we just got a couple of minutes left. Thank you all very much for joining. Some really interesting discussions. Does anyone have any final points? Anything else they want to say? I think they've missed. And if not, we can leave the room and go back to the main room. In the top of the chat, there's a link to the main chat. It's about halfway up from Age. No, perfect. Again, thank you all. Really interesting, and I'll see you all back in the main room shortly.
Yeah,
after
thank you.
coffee.
Thank you, Dan.
Thanks all.
Thanks, Dan. Bye.
Thank you.